For nearly 40 years, one of the strangest readings any spacecraft has ever sent back sat quietly in NASA's archives, unresolved, occasionally cited, mostly just accepted as one of the solar system's unexplained oddities. Uranus was supposedly radiating almost as intensely as Jupiter, one of the most violently dangerous planets in the solar system, while somehow being nearly empty of the material that should have been powering that radiation in the first place. Two facts that flatly contradicted each other, both measured by the same spacecraft, during the only close look humanity has ever gotten at that planet. This is the real story of what happened when NASA scientists finally went back and reanalyzed that decades-old Voyager 2 data properly, what they found waiting there, and why the answer is a lot stranger, and honestly a lot more reassuring, than the word terrifying in a headline usually implies. Before we get into it, if you're new here, this channel covers space and astronomy stories the way working scientists actually talk about them, without the exaggeration. If that sounds like your kind of channel, the subscribe button is right there, and it genuinely helps this content reach more people who care about getting the science right. Let's start with why this one flyby carries so much weight in the first place. In January 1986, Voyager 2 swept past Uranus, and to this day, it remains the only spacecraft that has ever gotten a close look at that planet. Everything humanity currently knows about Uranus up close, its rings, its tilted sideways rotation, its collection of moons, comes from that single pass, captured over the course of a few hours as the spacecraft sailed through on its way toward Neptune. There's been no orbiter, no follow-up mission, nothing since, whatever Voyager 2 measured during that brief window has effectively functioned as the entire scientific record for an ice giant planet for the past 40 years, and what it measured didn't quite make sense. Alongside genuine discoveries, 10 new moons, 2 new rings, Voyager 2's instruments detected something inside Uranus's magnetosphere that immediately troubled scientists. A magnetosphere, for context, is essentially a protective bubble generated by a planet's magnetic core, the same kind of structure that shields Earth from the stream of charged particles constantly blasting out from the sun and the solar wind. Inside Uranus's version of that bubble, Voyager 2 found electron radiation belts with an intensity second only to Jupiter's. And Jupiter's radiation belts are famously, notoriously brutal, powerful enough that spacecraft have to be specifically hardened against them just to survive a close pass. Finding something nearly that intense around, a much smaller, much colder, much more distant planet was already strange on its own. But here's what made it genuinely baffling, rather than just impressive. Those radiation belts need a source, a steady supply of energized particles feeding into them to keep them charged up. And when scientists looked at the rest of Uranus's magnetosphere for exactly that kind of source, they found almost nothing. The bubble was, by their measurements, nearly empty of plasma, the ionized gas that should have been the fuel supply for those belts in the first place. It's a bit like finding a roaring bonfire in a room with no visible source of kindling anywhere nearby. The two readings directly contradicted each other, and nobody had a clean explanation for either half of the contradiction on its own, let alone both at the same time. It got stranger still once you factored in Uranus's moons. The planet has 5 major moons sitting inside that same magnetic bubble, and researchers already knew from studying other icy moons around the outer planets that objects like these typically release water ions into their surrounding environment, evidence of ongoing geological activity, cracks, plumes, some kind of internal churn happening beneath their icy surfaces. But if Uranus's magnetosphere was nearly empty of plasma, and the moons should have been contributing exactly that kind of plasma, the only conclusion available to scientists at the time was that all 5 moons had to be geologically dead. No activity, no internal churn, essentially frozen inert chunks of ice drifting in orbit. That became the accepted scientific conclusion for decades, baked into essentially every textbook description of the Uranian system that followed, a direct consequence of what one brief flyby appeared to show. Now, here's where the story picks up in the present. A team led by Jamie Jasinski at NASA's Jet Propulsion Laboratory went back through the original Voyager 2 data, not with new instruments, the spacecraft is long past Uranus and can never return, but with decades of improved understanding about how magnetospheres and solar wind actually interact, tools and models that simply didn't exist back in 1986. What they found, published in the journal Nature Astronomy, was that the entire contradiction had a single, almost embarrassingly simple explanation hiding in plain sight the whole time. It just required looking at conditions in space during the days immediately before the flyby, rather than only the moment of the flyby itself. In the days leading up to Voyager 2's arrival at Uranus, the planet had been hit by an unusually intense burst of solar wind, a genuine space weather event. That event slammed into and compressed Uranus's magnetosphere, squashing the protective bubble down from its normal resting state. And that single piece of context, once accounted for, resolves both halves of the original mystery at the same time. The compression event would have driven plasma out of the system entirely, physically pushing the ionized gas out of the bubble, which explains why Voyager 2 found the magnetosphere looking nearly empty. And that same violent compression would have briefly and dramatically intensified the internal dynamics of the magnetosphere, injecting a fresh surge of energized electrons directly into the radiation belts, which explains why those belts were reading almost as intensely as Jupiter's. Two seemingly contradictory measurements, both produced by the exact same brief freak event happening at exactly the wrong, or depending on how you look at it, exactly the right moment. Jashinsky put the actual rarity of that timing in stark terms. In his own words, if Voyager 2 had arrived just a few days earlier, it would have observed a completely different magnetosphere at Uranus. He went on to note that the spacecraft saw Uranus in conditions that only occur about 4% of the time. Sit with that figure for a second, because it's really the heart of this entire story. Humanity's only close-up snapshot of an entire planet's magnetic environment happened to be taken during a genuinely unusual 4% window, a brief spike in solar activity that just happened to be underway at the exact moment the one spacecraft we ever sent there flew through. Every conclusion drawn about Uranus's magnetosphere for the past 40 years was, in a very real sense, built on top of that one unlucky or lucky coincidence of timing. Linda Spilker, who was one of the Voyager 2 mission scientists actually watching the data come in live back in 1986, and who has since returned to lead the mission's science team as project scientist decades later, put the significance of this reanalysis plainly. In her words, the flyby was packed with surprises, and the team was searching for an explanation of its unusual behavior at the time. The magnetosphere Voyager 2 measured, she said, was only a snapshot in time. This new work explains some of the apparent contradictions, and it will change our view of Uranus once again. That's a genuinely remarkable thing for a scientist who was there for the original measurement to say about her own mission's data nearly 40 years later. And here's why the actual headline word terrifying doesn't really hold up once you understand what this reanalysis means. And it's worth being direct about that, rather than just chasing the dramatic framing. This isn't a discovery of some new threat or hidden danger lurking around Uranus. It's the opposite kind of story, a correction and genuinely a hopeful one. If the missing plasma in Uranus's magnetosphere was simply blown out by a temporary solar wind event rather than being permanently absent, because the moons were geologically dead, then the original conclusion that all 5 major Uranian moons are frozen and inert may simply be wrong. Researchers now say it's entirely plausible that some or all of those moons have actually been spewing ions into their surrounding environment all along, evidence of genuine ongoing geological activity that the 1986 data, skewed by an unlucky 4% solar wind event, simply couldn't detect at the time. That's not a scarier universe. That's a solar system that just quietly got more interesting, with real open questions about whether some of Uranus's moons might harbor the same kind of subsurface activity scientists have found evidence for at icy moons around Jupiter and Saturn. It's worth being honest about what this reanalysis doesn't do too, because that's exactly the kind of caveat this channel tries not to skip. This isn't new data. Voyager 2 can never fly past Uranus again. It's long gone deep in interstellar space, and nothing about this reanalysis changes what instruments were actually pointed at the planet in 1986, or what they were capable of measuring in that moment. What changed is entirely the interpretation, built on better models of solar wind behavior and magnetospheric physics, that simply didn't exist when the original data came in. That's a real legitimate scientific advance, but it's a correction to our understanding built from old measurements, not a fresh discovery from new ones, and it's worth being precise about that distinction rather than blurring it for a more dramatic headline. This particular story also fits into a much broader ongoing pattern with the Voyager missions that's genuinely worth knowing about. Both Voyager 1 and Voyager 2 launched in 1977, flew their primary planetary tours by the late 1980s, and have spent the decades since drifting steadily outward, first through the solar system and eventually past its edge entirely into true interstellar space. Voyager 2 crossed that boundary, called the Heliopause, in November 2018, becoming just the second human-made object ever to leave the Sun's direct influence, following its twin by about 6 years. It's now nearly 13 billion miles from Earth, still transmitting, still functioning on a radioisotope power supply that loses a little more output every single year as the plutonium inside it steadily decays. NASA engineers have had to make increasingly difficult choices about which instruments to keep running as that power margin shrinks, and as recently as this past week, the mission team pulled off a clever power-saving maneuver, informally nicknamed the Big Bang, that's expected to buy Voyager 2's 3 remaining active instruments at least another full year of operation before anything else has to be switched off for good. That context matters here because it means the well of old Voyager data isn't actually closed, even though the spacecraft themselves have moved on decades ago from every planet they'll ever visit. Every byte of information both Voyagers ever transmitted from Jupiter, Saturn, Uranus, and Neptune sits permanently archived. And as this Uranus reanalysis demonstrates, scientists are still actively finding genuinely new conclusions, buried inside data that's been sitting untouched, or at least unresolved, for nearly 40 years. The tools for interpreting that old data keep improving, even though the data collection itself stopped decades ago, which means there's a real ongoing possibility that other unresolved anomalies from those same flybys, oddities in the Neptune or Saturn data that never got a clean explanation either, could eventually get the same treatment this Uranus mystery just received. So here's why any of this should matter to you beyond the fact that it makes for a good story. Understanding how magnetospheres actually behave isn't just an abstract curiosity about one distant ice giant. It directly shapes how scientists plan future missions. And Uranus, specifically, was named a top priority target by the National Academy's 2023 Planetary Science and Astrobiology Decadal Survey, the document that effectively sets NASA's long-term exploration priorities for the coming decade. A dedicated orbiter mission to Uranus, something that's never happened before, would finally be able to observe that magnetosphere across many different solar wind conditions, rather than catching one brief, unrepresentative 4% snapshot the way Voyager 2 unavoidably did. And understanding magnetospheres more broadly matters well beyond our own solar system too, because the same physics governing how a planet's magnetic bubble protects or fails to protect whatever orbits inside it is directly relevant to scientists trying to assess habitability around exoplanets circling other stars entirely. If you've stuck around this long, you already know this isn't the kind of story with a tidy villain or a genuine threat sitting at the center of it, and I'd rather tell it straight than dress it up with a scarier word than the actual science supports. What's actually here is something quieter, and once you sit with it, more remarkable. A single freak coincidence of timing, a 4% chance solar storm arriving in exactly the wrong week, shaped humanity's entire understanding of an entire planet for nearly 4 decades. And it took this long and this much improvement in modeling technique for anyone to finally catch it and correct the record. If this kind of deep dive into real sourced space science is what you come here for, subscribing helps a lot. Let me know in the comments whether you think one of Uranus's moons is genuinely active down there and what you'd want a real Uranus orbiter mission. To check first, if NASA ever actually builds one, it genuinely shapes what we cover next. And sharing this with someone who'd get a kick out of it is the easiest way to support the channel.